The sun is not going to go cold. That needs to be said first. The sun has approximately 5 billion years of hydrogen fuel remaining. It is operating exactly as it should, and there is no mechanism in known physics by which a star of its size and age could suddenly stop producing heat. But here is the question that actually matters. If it did, if some impossible event froze the sun's fusion reactions in a single instant, how long would you have? What would happen first? What would happen last? And is there anything in this scenario that does not end in death? The answers are stranger, more specific, and more terrifying than most people expect. 8 minutes and 20 seconds of not knowing nothing would happen immediately. Light travels at approximately 300,000 kilometers per second. The average distance between the Earth and the Sun is approximately 150 million kilometers. Dividing one by the other gives you about 8 minutes and 20 seconds, the amount of time it takes for sunlight to reach Earth. If the sun went cold right now, the last light it ever produced is already on its way to you. For the next 8 minutes and 20 seconds, the sky would look completely normal. The sun would appear exactly as it does every other day. You would have no way of knowing anything had changed. This applies to gravity as well. Gravity, according to general relativity, propagates at the speed of light. For those same 8 minutes and 20 seconds, Earth would continue orbiting as if the sun were still there. Every calculation, every trajectory, every gravitational tether would remain intact. Then both would stop simultaneously. The light would cut out. Not like a sunset, not gradually, but completely. Total darkness in the middle of the day, as though someone turned off the sky. And at that exact same moment, Earth's gravitational bond to the sun would snap. The planet would stop curving through its orbit and instead continue in a straight line at its current orbital speed of approximately 30 kilometers per second, heading out into interstellar space. You would have 8 minutes and 20 seconds of complete normalcy before the universe changed permanently. That window is the most unsettling detail in the entire scenario, not because of what happens in it, but because of what is coming that you cannot see. Within the first hour, the stars come out at noon. The immediate visual effect would be total. The moon, which produces no light of its own and shines only by reflecting sunlight, would go dark at the same moment as the sun. The sky would be lit only by stars. Exactly the same stars visible at night, now visible at noon against a black sky. The temperature would not drop immediately. The atmosphere holds heat. The oceans hold enormous amounts of heat. The ground itself retains warmth. In the first hour, you would not feel the cold. What you would feel is the absence of the sun in every way that is not temperature. No UV radiation, no infrared, no light for photosynthesis, no signal for the biological clock systems of every organism on Earth, including humans, that synchronize to the light-dark cycle. The psychological impact of permanent global darkness, arriving with no warning and no explanation, would be the first human crisis. Not cold, not food, darkness, and the certainty that it is not temporary. Within the first week, the freeze begins. This is where the numbers become specific and they become brutal. Without solar input, the surface temperature of the Earth would drop by approximately 20 degrees Celsius every 24 hours in the early stages, according to physicist estimates reported by Live Science. The average global surface temperature today is approximately 15 degrees Celsius. Within the first day, it drops to around -5. Within 3 days, -45. Within a week, the average global surface temperature would be below -40 degrees Celsius. To put that in context, the coldest temperature ever recorded on Earth's surface was -89.2 degrees Celsius at Vostok Station in Antarctica in 1983. Within 2 weeks, that would be the average surface temperature globally. Plant life would collapse almost immediately. Photosynthesis requires light. Without light, it stops within hours. Most surface plants would begin dying within days to a few weeks, exhausting their stored sugars. Large trees with massive energy reserves and slow metabolisms could survive for several decades in the dark, but not the cold. Their water and sap would freeze long before they starved. Herbivores would follow within weeks to months as the food supply vanished. Predators would follow them. The food chain would collapse from the bottom upward with a speed proportional to how dependent each organism was on surface plant life. Within the first year, minus 100 degrees Celsius. After approximately 1 year without solar input, the average surface temperature of the Earth would stabilize around minus 100 degrees Celsius, colder than anywhere on Earth's surface has ever been recorded, colder than Mars in winter, colder than the poles of the Moon. The oceans are a different story, and this is one of the counterintuitive details that matters. The oceans contain an enormous amount of thermal energy. Water has one of the highest heat capacities of any common substance. It absorbs and holds heat far more efficiently than air or rock. The surface of the oceans would begin freezing over within weeks, forming a layer of ice. But that ice layer would act as an insulator, slowing the heat loss of the deep water below it dramatically. According to researchers at the California Institute of Technology, the deep oceans would not freeze solid for hundreds of thousands of years. Beneath miles of surface ice, liquid water would persist, dark, cold, pressurized, and cut off from all sunlight, for an extraordinarily long time. This detail is important for a reason we will return to. Within the first decades, the atmosphere begins to collapse. As temperatures plunge further, the atmosphere itself begins to change. Nitrogen and oxygen, which make up approximately 99% of Earth's atmosphere, remain gaseous even at extremely cold temperatures. Nitrogen liquefies at minus 196 degrees Celsius. Oxygen liquefies at minus 183 degrees Celsius. These are temperatures the surface would not reach for an extremely long time. But carbon dioxide behaves differently. Carbon dioxide freezes, deposits directly from gas to solid, at minus 78.5 degrees Celsius at normal atmospheric pressure. As global temperatures drop past this threshold, carbon dioxide in the atmosphere would begin to condense and precipitate out. It would snow carbon dioxide. Solid dry ice would fall from a sky that no longer has a sun. Carbon dioxide makes up approximately 0.04% of the atmosphere. Losing it would not immediately suffocate anyone. Oxygen would remain for approximately 1,000 years, even without replenishment from plants. But carbon dioxide is the primary greenhouse gas that has kept Earth's temperature in a livable range for billions of years. Removing it from the atmosphere would accelerate the cooling further, driving temperatures down even faster. The atmosphere would not collapse quickly, but it would collapse. What humans could do, and how long it would work. Survival would require abandoning the surface almost entirely. The most viable long-term option identified by scientists studying this scenario is geothermal energy. Earth's core remains molten from the residual heat of planetary formation and the ongoing radioactive decay of elements like uranium, thorium, and potassium in the mantle. This internal heat is entirely independent of the sun. It is not going anywhere. Iceland already heats approximately 87% of its homes using geothermal energy. The volcanic regions of the planet, Iceland, Japan, New Zealand, parts of the western United States, would become the most strategically valuable locations on a frozen Earth. Underground habitats drawing heat from geothermal sources, lit by artificial lighting, growing food in sealed environments. This is the survival scenario. Not comfortable, not sustainable at the scale of the current human population, but physically possible for smaller groups, potentially for centuries. Nuclear energy would supplement this. Nuclear reactors do not require sunlight to function. A functioning reactor network could power heating, lighting, and food production independently of the sun for decades or longer, constrained only by fuel supply and infrastructure maintenance. The realistic assessment from astrophysicist Ethan Siegel is direct. This would be an extinction event that makes all previous ones in Earth's history look minor. The majority of complex surface life would be gone within years. A remnant human population might survive for decades to centuries in geothermal shelters. But the timescale of recovery, the restoration of a livable surface environment, would require another star, another orbit, another energy source, none of which would arrive. The life that would survive. And for how long? Here is the detail that reframes the entire scenario. Deep beneath the ocean surface, at depths where no sunlight has ever reached, exist ecosystems built entirely around hydrothermal vents, cracks in the ocean floor where geothermal heat drives superheated water and dissolved minerals upward. The organisms at the base of these ecosystems are chemosynthetic. They extract energy from chemical reactions with hydrogen sulfide and other minerals with no dependence on sunlight whatsoever. These ecosystems would survive, not just for years, potentially for billions of years. As long as the Earth's core remains hot enough to drive hydrothermal activity, and as long as the deep ocean remains liquid, these communities would persist. The insulating ice above them, the geothermal heat below them, the complete isolation from everything that killed the surface, all of it would actually protect them. Similarly, deep underground microbes, living kilometers below the surface in rock formations and extracting energy from mineral chemical reactions, would continue operating almost entirely undisturbed. They live on geological timescales. The sun going cold would barely register in their biology. The most complex, most intelligent, most technologically sophisticated species in Earth's history would be gone within decades to centuries. Microscopic organisms that have never seen sunlight and do not need it would carry on for billions of years. The final state. What Earth becomes. Over millions of years, the cooling stabilizes at approximately -240 degrees Celsius. The point at which the heat generated by Earth's core and the radioactive decay of its interior equals the heat Earth radiates into space. This is approximately the same surface temperature as Pluto. Earth would become a rogue planet, a frozen dark sphere traveling through interstellar space at 30 kilometers per second, no longer bound to any star, carrying a liquid ocean beneath miles of ice and a living biosphere in the darkness below. The atmosphere would compress and partially collapse over millions of years as more gases condensed and froze onto the surface. The surface would be a landscape of frozen nitrogen, frozen oxygen, frozen carbon dioxide, a planet that preserved, in its ice, all the chemistry of a world that once had a sun. And beneath all of it, in the dark water above the vents, life would continue. Not our life, not anything we would recognize, but life. The most fundamental definition of life, chemical systems that extract energy from their environment and replicate, would still be happening on Earth billions of years after the sun went cold, in the deepest, darkest, most pressurized water on a frozen rogue planet drifting through the galaxy. That is either the most hopeless or the most remarkable ending to this scenario, depending on how you look at it. The sun keeps everything on this planet alive. Every calorie you have eaten, every breath you have taken, every warm day you remember. All of it is borrowed energy from a fusion reaction 150 million kilometers away. The moment that reaction stops, the clock starts. And 8 minutes and 20 seconds later, you would finally see it.